In this topic, we're going to study the Fourier series of functions that are not periodic. Now, this is a very important idea that has applications in image processing, and in particular in facial recognition software and in robotic vision. Now, to see this, we have to think about an image as a function. So let's start with an image. So here's a picture of me. How can I think of this as a function? Well, every pixel of this image is associated with three numbers, one for red, one for green, and one for blue. I could look at just the red part of this image and get a 2D scalar field that tells me how much red is in each pixel, with values ranging from 0, no red, to 1, which is all red. I could do the same for the green part of the image or the blue part of the image. So each of these red, green, and blue images is a 2D scalar field. But let's keep things simple. Let's just look at a black and white version of this image. Now I have a 2D scalar field that tells me how bright or dark the image is at each pixel. This is a function of x and y, and I can analyze it using Fourier series. To see this, imagine drawing a line from left to right and plotting the brightness of the image along this line as a function of the x-coordinate. I've slightly modified the function by shifting it down by a half. So now the function varies in values from -0.5 to 0.5, corresponding to dark or bright. Now this is clearly not a periodic function, but I can make it periodic by repeating this basic tile again and again. We now have a periodic function, and I can calculate the Fourier series for this function. However, we've seen that it's much more convenient to calculate Fourier series for odd or even functions. So instead, let's make an even periodic function. We'll do this by flipping our basic tile from left to right. The result looks something like this. So 2 Shanes for the price of 1. You can see that the plot of brightness as a function of the x-coordinate is now an even function. If I flip it left to right, I get the same function. And the Fourier series of this function will only involve cosines. Now we could also create a periodic function with odd symmetry. Have a think about what this might look like. Shane's evil twin. Now, why didn't we flip the image upside down? That's because the vertical coordinate of our function is not in the y direction, it's the brightness of the image. So flipping up down corresponds to swapping dark with light. The brightness as a function of the x-coordinate is now an odd function, and its Fourier series will only involve sines. Whether or not we make the function symmetric, we can now calculate its Fourier series. To see what this would look like, imagine that we can reconstruct this function by adding back in one Fourier component at a time. Now, as you can see, the Fourier series, which is shown in blue, starts off quite smooth, but slowly converges to the actual function. Now let's apply these ideas to our original image. Again, I'm going to reconstruct the image by adding in one Fourier component at a time. Since I'm doing this numerically anyway, I'll actually do the calculation for the red part of the image, for the green part of the image, and for the blue part of the image, and in both the x and y directions, so that I end up with a 2D color image. Again, you see that the Fourier series starts off very smooth and slowly adds in finer and finer scale detail until we finally get the original image back again. Now, if I had stopped adding in Fourier components at some point, I would have ended up with a smoothed version of this image. So maybe something like that. Now this is called a low-pass filter. It only includes the lowest frequencies, which are the smoothest features of the image. So that's called a low-pass filter. On the other hand, I could do the opposite. I could look at what's left over when I remove all of these low-frequency components of the image. This is called a high-pass filter. It only contains the parts of the image where there are high frequencies, that is, when there's sudden changes, like near edges in the image. As you can see, the image looks pretty strange, but features like the edge of the crest here, the writing, and my face are much clearer in this image than they are in the low-pass filtered image. This idea of using high-frequency Fourier components is used in facial recognition software and in robot vision to help automatically identify faces or edges in images.